Okay, let's get started. As usual, we'll come back to this problem a little bit later in class. So keep it in mind, and we will solve it at the end of the hour. Let's start out with some announcements. It's really just, again, a reminder that the problem set is due at 11:59 p.m. Montreal time on Friday. That's this Friday. And you should submit that again via My Courses if you can. That's for registered students. And then otherwise you can submit it by email to me and the TA. And I really do encourage everyone to post in the Slack if you're looking for collaborators, or just if you're confused about something. That is what collaborators are for. It's something that you should do if you feel like you don't understand a problem, if you feel like there's some part of your solution that you don't understand. Collaboration is encouraged. Find somebody else or a couple of people and start a small group discussion in the Slack or over video chat to work out what's going on with the problems. And then also, I do encourage you to go to office hours. So Vincent's office hours are tomorrow at 10:30, and mine are on Friday at 10 a.m. Both of those are Montreal time. So again, really encourage you to find other people to talk to if you're confused about any or all of the problems, and likewise, come talk to me. You can also send me Slack messages if you want. Are there any questions about anything? For the problem set, is it okay to discuss specifics, e.g. what particular monovariants you might be using if you were using a monovariance approach for a problem, beyond general strategies? It's totally okay to discuss that with your collaborators. Please don't post to the entire Slack, because that's like giving an idea for a solution to everybody. But with your collaborators, you can certainly discuss that. It's just you shouldn't give any kind of written material to your collaborators, because the proofs need to be written completely by yourself. But you can definitely iron out specifics of the monovariants with your collaborators. There's a spot on the problem set for listing your collaborators. Make sure you do that. But that's sort of the point of why you would have collaborations. Please don't have massive collaborations. Like, shouldn't be like 20 people in a collaboration, because then not everyone is really participating. But for a few people, yeah, absolutely. Should collaborations be cliques? I mean, doesn't have to be pairwise connections. I'm assuming that question's a little bit tongue-in-cheek anyway. But they should be relatively small. Cliques in this sense was probably a reference to the graph theoretical definition. How long do the office hours last? They are each 1 hour. Feel free to come at any point during office hours. Though I do encourage you to come earlier on, just because if there are a lot of questions, might take a while to get to your question. Any more questions? Okay, great. Let's actually dive into the class for today. And so today, as I noted in last class, it was going to be something different, but we're pushing a couple of classes back. I wanted to talk about polynomials and algebra and complex numbers and inequalities today. So that's what we'll be discussing this class. And then in 2 classes, we'll go back to the schedule. Next class, we'll be discussing some number theory. So let's start out with what is a polynomial. So probably many of you have seen polynomials before. A polynomial in a variable is just an expression that looks like this, where you have some coefficients in front of your variables, and the variables are raised to different integer exponents. So here you have an x to the n term, an x to the n minus 1 term, all the way down to x squared, x, and a constant term. And those constants are called coefficients. We'll generally be working with real polynomials, so polynomials where the coefficients are real numbers. You can have a polynomial in a variable x, or in any other variable. You can have a polynomial in t or y or theta or so on. The number n is called the degree of the polynomial. And n is importantly, in the case that we're considering at least, going to be some non-negative integer. So it's going to be 0, 1, or anything greater than 1. So some examples of polynomials. In the case of degree 3, it's called a cubic polynomial. So here you would have the leading term would be 2x cubed, for example. If it's degree 2, it's called quadratic. That's an example of a degree 2 polynomial. If it's degree 1, it's called linear. And if it is degree 0, it is a constant polynomial. And that is a perfectly legitimate polynomial. Okay. And you can also talk about the quadratic term or the linear term, which would just be that degree term within a polynomial. So multiplication and division of polynomials. If you have two polynomials that are degree m and n respectively, so m is the degree of p and n is the degree of q, then the degree of their product is going to be m plus n. Some of the inner terms might cancel out, importantly. If you're multiplying polynomials, some of the inner terms might cancel out, but the first term, the leading term, that is always going to multiply together with the other leading term, and you're going to get something which has degree m plus n. That's sort of important. So here's an example. If you're multiplying these two polynomials, you had a linear polynomial, degree 1, and a cubic polynomial, degree 3. You get this quartic polynomial, degree 4. And yeah, you can just do the multiplication. Here it's just x times this. So that gives you these terms, and 1 times this. And yeah, or the x times this, and that gives you this term and this term. 1 times this, and that gives you this term and this term. Obviously, sometimes polynomial multiplication is a bit more difficult than that. We're not really going to be going into the algebra of it. This is just a review of some important facts. Division. If you have two polynomials with degree m and n respectively, then we can write, if the first degree is bigger than the second degree, the degree of p is greater than the degree of q, then you can write p as some multiple of q plus a remainder term. So it's a multiple of q with a polynomial multiple of q. There's some polynomial r of x and some remainder polynomial s of x, where p is equal to q times r plus s. And then an important thing here is that the degree of f is strictly less than n. It's strictly less than the degree of q. So you can sort of deal with everything up to degree n by picking r appropriately, but then there's going to be something left over, which is s. So as an example here, if you had p equal to this cubic polynomial and q equal to this quadratic polynomial, then you have p is going to be some multiple of q, and we're going to have to deal with every term in here up to degree 2. So here we're going to have the multiple of x squared plus x. I'm not expecting you to get exactly why this works, but the multiple that we would get of x squared plus x, we need to deal with all the cubic terms. So how are we going to deal with the leading term? We're going to have 2x, so 2x times this. That'll give us this leading term. But then we have 2x times x, and so that would give us a 2x squared. And so we need to cancel that out, so minus 2. And so we have 2x cubed plus 2x squared minus 2 times this, which is 2x squared plus 2x. And so if you calculate this out, you see that this works for the cubic term, it works for the quadratic term, which is 0, and then there's something left over, which is, in this case, just a linear term, 4x plus 1. So the remainder in this case has degree 1. It's degree strictly less than the degree of q. In this case, yeah, that means it's a linear remainder. Are there any questions so far? Okay, so why is this called division? Great question. So this is division in the same way as like division of integers if you never knew that rational numbers existed. So you could say that like 8 divided by 3 is 2 with a remainder of 2. This is sort of going back to like elementary school arithmetic. But with polynomials, I mean, there is a completion of the polynomials where you're allowed to have quotients of polynomials, but they're no longer polynomials. So if you were trying to like actually divide p by q, you couldn't do it and get a polynomial out. So you're going to have to get a polynomial out plus a remainder, if that makes sense. Why do we want s of x's degree to be less than n? You will see an example of that in a moment. Why it's good to have the remainder. I mean, this is just a fact, right? Like, it's not like you're good. I'm not going to ask you to do polynomial division. This is just something that you should know, that if you wanted to divide a polynomial by another polynomial, you could do it, but you would get a remainder term that is degree less than the thing you're dividing by. In the same way as the remainder, when you're dividing by 3, is going to be less than 3. If you divide 8 by 3, you get 2 with a remainder of 2. Or the remainder of 2 has to be less than 3. If it were greater than or equal to 3, you could take another 3 away, if that makes sense. So this is sort of the analog of remainders in just integer division. Okay, so one of the reasons why this will be useful for us is in looking at roots. So a root of a polynomial p of x is a value of x such that p of x equals 0. So linear polynomials are pretty easy to find the roots of. For example, if you had 2x plus 4, when is that equal to 0? Well, it's pretty easy to see that if you set x equal to -2, then that's going to evaluate to 0. Okay, so that's a root, and it's the only root of 2x plus 4. Now, here is an important theorem. It is perhaps intuitive, but it's really deep. A polynomial p of x is divisible by x minus r if and only if r is a root, where I mean divisible in that there is no remainder. Why is this true? How can you prove it? Okay, we can substitute in. That only goes one way. So people are suggesting you can, suppose you wrote in p of r. Well, if p of r is some multiple of, if p of x is some multiple of x minus r, then if you substitute in r, you get some multiple of r minus r, which is 0. And so if it's divisible by x minus r, then r is a root. Now, here's the harder part. If r is a root, why is it divisible by x minus r? Isn't it possible that it could be equal to 0, that p of r could equal 0, but p of x could not be divisible by x minus r? This if and only if, this is often a thing in math. It means if this is true, then this is true, and if this is true, then this is true. And they're not the same thing. If the polynomial is divisible by x minus r, it's pretty easy to show that p of r is 0, so r is a root. But suppose r is a root, why does that mean that p of x is divisible by x minus r? Mm-hmm. Yeah, so let's try doing that division. Let's try doing that division. To answer some of the questions, I'm not quite sure what is suggested by roots are invariant to translations. So I'm happy to discuss that separately. We assume that there is only one root. The polynomial might have many roots, so it's not, unfortunately, possible to assume there is just one. But like, I'm going to take the suggestion of dividing p of x by x minus r. So here we're dividing with remainder. So we don't know that it's divisible by x minus r, but we know that we can divide it with remainder, regardless of whether it's divisible or not. So p of x equals q of x times x minus r plus some remainder s of x. And in particular, the remainder s of x has degree less than the degree of x minus r, because we were dividing by x minus r. So what is interesting here? Why is that useful? Ah, so S has a degree less than x minus r. But what's the degree of x minus r? Well, x minus r has degree 1. So S of x has to have degree 0. And a degree 0 polynomial is just a constant. So we can write this as just a constant S. Okay, so what's the constant? Well, if we set x equal to r, we have p of r equals q of r times r minus r, which is 0, plus s. So p of r equals s, regardless of whether p of x is divisible by x minus r, p of r is equal to s. So that means that these two are equivalent. It's not just the case that the implication goes one way, it goes both ways. If p of x is divisible by x minus r, then s equals 0. There's no remainder. And that means that p of r equals 0. That was the thing we already knew. But going the other way, the thing we didn't already know is that if r is a root, that means that p of r equals 0, and so s equals 0. And that means that p of r is nicely divisible by x minus r. Does that make sense? We're proving it both ways. Are there any questions? So these are some of the, when you're finding some new math, there are these really basic questions, even if you're like thinking back to some old math that you already learned. There are these really sort of basic questions, which is always really good to sort of question the assumptions of. Like, even if you know that a fact is true, just really understanding why it is true is really important. Sometimes you'll find some of these basic facts are actually really, really difficult to prove. And there's some like complicated math involved. Here, this is like semi-complicated math. Yeah, okay. So now we saw how to solve linear polynomials. It's pretty easy to find the roots of a linear polynomial. What about a quadratic polynomial? So here's this famous thing that you might have learned in elementary school or middle school or high school. I don't know I don't remember when it's learned. Quadratic formula. You have a quadratic polynomial, and it has roots given by x equals to this mess. You can just plug in whatever the coefficients are, and you'll get some answers. This plus or minus means that it has two roots. One of them is this with plus, and one of them is this with minus. How would we prove this? In particular, I want to prove both directions, that these are roots and that there are no other roots. So we can set the equation to 0 and solve, I agree. That wouldn't prove that there aren't any other roots. How do we prove that there aren't any other roots? We could do it by contradiction. We could do it by contradiction. But there's a sort of faster way. Yeah, so a couple of people are suggesting sort of factoring it. So we have this previous theorem, right? We have this previous theorem saying that the polynomial is divisible by x minus r if and only if x is a root. So we can just factor this polynomial. Now I am going to gloss over something, which I'll say in a moment. We just need to check that if we do x minus root 1 times x minus root 2, then we get the polynomial. So we've divided nicely by, we have these two linear factors, and we get the polynomial. And we can just do the algebra for that, and that shows that these are roots, and it also shows that these are the only roots, though I'm glossing over something, which is is polynomial factorization unique? Like, is there only one way to write this as the product of two linear polynomials? And that is correct. In fact, that is true, but it's not something that I'm going to prove because it's difficult to show that polynomial factorization is unique, or it's more complicated at least. So some people were saying, don't we know that a polynomial with degree n has exactly n roots? And that is true, and we'll get to that in just a few slides. So we would expect a quadratic polynomial, so one with degree 2, to have 2 roots, and one with degree 3 to have 3 roots, and so on. And we'll get to that in a moment. So when are the 2 roots equal? I just want to go through this quadratic formula a little bit more. The 2 roots are going to be equal if this thing in the square root is 0, because then plus it and minus it are the same thing. And then you have b squared minus 4ac equals 0. So for example, if you had x minus 3 squared, which is this quadratic polynomial, x squared minus 6x plus 9, in that case, b squared minus 4ac is 36, so minus 6 squared, minus 4ac, so 4 times 1 times 9 is 36. 36 minus 36 is 0. This thing is called the discriminant, so the discriminant is 0. So you end up with, this is a double root, and it's x minus 3, this is x minus 3, and this is also x minus 3. You have two roots. Okay. So now I'm going to dive into the situation where this thing is actually negative instead of being 0. And in this case, we're going to have to deal with complex numbers. Can there be no roots? It is not possible for there to be no roots of a polynomial. And we will get to that in a moment, but a polynomial will have to have n roots. But those n roots might not be real numbers. They might be these complex numbers. So in order to look at complex numbers, we're going to have to define the imaginary unit, I, and it is equal to the square root of -1. And this is super, super important throughout math. And we will just keep on seeing ways in which it's important. And even though it's imaginary, it's like really useful in practical math too. It's not just like something that theoretical mathematicians care about. So a complex number is a number of the form a plus bi, where a and b are real numbers. So we have this imaginary unit, and we have like sort of the real part and the imaginary part of a complex number. To work with complex numbers, you should treat I like it's some variable x, sort of. But if you ever see I squared, then you know you can substitute -1, because I is the square root of -1. And there's actually like formal math that makes this like perfectly rigorous, and all of the axioms of math work out nicely. I'll sort of let you take my word for it there. But if you want to investigate that more, I can point you to some resources. So how do you do like addition with complex numbers? Well, a plus bi plus c plus di, so these are 2 complex numbers. You just add the real parts, just add the imaginary parts. And what do you do if you multiply together 2 complex numbers? Well, let's treat them like 2 polynomials, where I is sort of like a variable. So then you would have AC, you would have bi times di, so bdi squared, and then adi and bci. And what do you do with this? Well, you're like, oh, I see I squared. Well, I'm going to substitute -1 in there. So I can make this be a real part, AC minus BD. And this is the imaginary part, AD plus BC. And so I have a new complex number where this is again real and this is again real. So you have the real part and the imaginary part, and AD plus BC is the real coefficient on the imaginary part. Question, what is I cubed? I'm seeing some disagreement here. So I cubed is equal to I squared times I. So it is equal to -1 times I, which is just -I, which is another complex number. It's just if you had A is equal to 0 and B is equal to -1. So I cubed is another nice complex number. It's just -I. And then likewise, I to the 4th is going to be I squared squared, which is -1 squared. And so it's just going to be equal to 1. So I to the fourth is actually 1, which is really weird. And we'll get into why, to some more nice ways to understand that in a few slides. So one of the most beautiful things about complex numbers is trigonometric form. And to understand this, let's think about what's called the complex plane. We often consider complex numbers, a plus bi, in the complex plane. That just means taking them as points in two-dimensional space where the x-coordinate a and y-coordinate b. So here is an example. Here the x-axis is the real part, that's why it's called r, and the y-axis is the imaginary part, that's why it's called here I. And you have a point that can be represented as a, b in two-dimensional space. Great. So we can also use polar coordinates. I'm not going to review polar coordinates. If you haven't seen them or hadn't seen them for a while, I'd go look up some polar coordinate stuff after the class. But the idea of polar coordinates is here just to use a radius, so distance from the origin, and angle theta, distance from the angle made with the x-axis to represent. So a plus bi can be written in polar coordinates as r times cosine of theta plus I r times sine of theta. So sine of r sine of theta is b, and r cosine of theta is a. So this is using polar coordinates r and theta to represent a complex number. Now, why would we be interested in this? Well, because there is this really beautiful thing. When you multiply complex numbers, it was really ugly when we used a plus bi sort of form. But if we're thinking about r and theta, a polar coordinate representation, then it becomes the best thing ever, which is the radii multiply and the angles add. So if you multiply something with radius r1 and angle theta1, and something with radius r2 and angle theta2, then you're going to get something with radius r1, r2, and something with angle theta1 plus theta2. Whoa, so cool. And there's no reason why this should be the case, like, just if you just, saw all the definitions before. So why is this the case? Now, there are different ways to see this. One way, like the really awkward way that you might have seen in school is proving this using trigonometric formulas. You can be like, okay, well, what is the cosine of theta1 plus theta2? Well, there's some formula for that in terms of cosine of theta1 and cosine of theta2 and sine of theta1 and sine of theta2. And you can do this multiplication and you're like, oh, well, this multiplied by this minus this multiplied by this gives you this. And that's true. And it is a perfectly reasonable way to prove this. But it doesn't really, so there's this notion in math of a proof from the book. A mathematician, famous mathematician, Paul Erdős, had the idea that there are these extremely elegant ways to prove math results that really explain to you why something's true. They don't just enable you to prove it. So logically, you know it's true. They also give you the right way of thinking about it. And in his words, these were, God had this book of math proofs, and it was called The Book. And he said that mathematicians didn't have to believe in God, but at least they had to believe in the book. So this is not the book proof of why multiplying complex numbers works like this trigonometrically. The book proof we will see, but we'll see it in a few lectures when we look at Taylor series. Do we get extra marks, a question asks, if we use proofs from the book? I mean, it'll make us happy if you make really good proofs of the problems on the problem sets. So certainly go for proofs from the book. It'll also make you happier. But there isn't always a really elegant proof of the problems on the P sets. I'm trying to make them be nice proofs. But no, they won't always be really beautiful. Okay, so what is 4i in trigonometric form? Question. So what's the r and what's the theta? Okay. Yep, so in a geometric way to think about this, you can think of this as being x equals 0 and y equals 4, so it's like somewhere along the y-axis. So the angle should be 90 degrees. Sorry, I guess I'm flipped here. The angle should be 90 degrees. And the radius is just 4 because it's 4 away from the origin. So that's the geometric way to think about it. The trigonometric way to think about it is you can like work out that this is true. So 4i is equal to 4 times cosine of 90 because cosine of 90 degrees is 0 and sine of 90 degrees is 1. And so you can just say that's the case. So two ways of thinking about it. You can just draw a picture, or you can think about it like, you know, what is going to give me 0 if I take the cosine of it. So what is 4i squared in trigonometric form? Okay, great. Yeah, so remember we add angles when we multiply things, and we multiply radii. So if we're multiplying 4i by itself, we multiply 4 by 4 to get the new radius, and we add 90 to 90 to get the new angle. So we must have the new angle being 180 degrees, and r equals 4 times 4 equals 16. And that makes sense because we know that 4i squared is going to be 16i squared, and that is going to be equal to negative 16. And if it's something is 180 degrees, then that means it's go all the way to the negative side of the x-axis. And so we end up with negative 16. So the geometry works out too. Cool. What's the square root of 4i? Cool. So we can write again 4i in trigonometric form. The radius is 4 and the angle is 90 degrees. We want some x equals, you know, with some r and theta, where if we square it, we get this. So we can have the radii multiply and the angles add. So we can have theta, we can have r equal to 2 and theta equal to 45. And cosine of 45 is square root of 2 over 2. Sine of 45 is the same thing. So we end up with this. Is that the only answer? So there are some suggestions of taking the negative of the angle. That's actually not going to work because then we would get cosine of negative 90 degrees. And cosine of negative 90 degrees is actually not the same, or sine of 90 degrees is negative 90 degrees is not the same as sine of 90 degrees. So we could actually have something else. We could have this, because if we add 360 degrees over 2 to this to get 225 degrees, then if we multiply this by 2, we're going to get 90 degrees plus 360 degrees. And the 360 degrees doesn't affect these because these are periodic with period 360 degrees. So you can have theta equals to 225 degrees. These are the only two answers. I've seen some suggestions of 180 degrees minus 45. That actually does not work. You can convince yourself later of why it does not work. But you can take theta equal to 225 degrees, and that will give you x equals negative square root of 2 minus square root of 2i, which sort of makes sense, right? Like if you multiply something by negative 1, you would expect it to square to the same thing. Just like two real numbers, if one is the negative of the other, they're going to have the same square. So likewise with two complex numbers, if one is the negative of the other, they're going to have the same square. Okay. Yeah, and if you tried to do 90 degrees plus 720 over 2, that would just give you 45 degrees again. It would give you 45 plus 360. So, I mean, look, there is, you can say that, you can write theta here as 45 plus 360, but the x that you get will be the same. So I'm really looking for the ultimate x here. The canonical way to write something in polar coordinates is with a positive radius and with an angle between 0 and 360 degrees. So that's what I'm going to be using to describe things. But you could also imagine this as like theta equals 45 degrees plus 360. Okay. Now let's go back to the quadratic formula. Now what happens if the stuff in the square root is negative? For example, we have this, where this is what happens if you plug stuff into the quadratic formula and you get square root of negative 16. Now we know now that we can write that as 4i. And so we have, in the end, negative 1 plus or minus 4i over 2. So negative 1 plus or minus 2i. We have two roots here of the quadratic. One is negative 1 plus 2i, and the other one is negative 1 minus 2i. And in general, complex roots of quadratics will come in conjugate pairs because of the quadratic formula. If there's one root, d plus ei, then there's another root, d minus ei. Because you always, when you get a complex number, it's because this thing is the complex part. Okay. Now here is a really important theorem, which I'm not going to prove because it's too hard. Every polynomial with real coefficients can be factored into quadratic and linear polynomials with real coefficients. So for example, if we had this polynomial, then we could factor it into, this here is a quadratic, here's a linear term, here's a linear term. We can't factor it into linear terms with real coefficients, but we can always factor it into quadratic and linear polynomials with real coefficients. So what's something that we get out of this? Oh, and yeah, the proof is unfortunately beyond the scope of this course, but you can look up the fundamental theorem of algebra if you would like to find out more. So a corollary is every polynomial with real coefficients and degree n has n complex roots. That's because we know that a quadratic polynomial has those two roots, which might be complex, given by the quadratic formula. So if you can factor it into something like this, well, you can factor, you know that all the linear polynomials give you real roots, and all of the quadratic polynomials give you two complex roots. And in particular, those complex roots are actually going to be conjugates of each other. So any real polynomial can be factored completely into linear factors if we're allowing ourselves complex number coefficients. So here we have a real coefficient out in front, and then we just write it as x minus r1, r2, and so on. These are the roots. They could be complex. If we have one complex number, then we have another one that is the conjugate pair. If the complex number, if the imaginary part is non-zero. So the only way we can get a complex number is from these quadratic polynomials. And since these quadratic polynomials have real coefficients, we know that the roots come in conjugate pairs. So if we have any complex root of any degree polynomial, we know its conjugate is also there. Question about polynomials with imaginary coefficients. So this theorem actually comes from a theorem saying that any polynomial with imaginary coefficients is going to have roots that are imaginary. So you can find n roots of a polynomial with degree n if the coefficients are complex. Now, something I'm not really talking about is these can be duplicates. So you could have x minus 1 squared, and that has the root 1 twice. So that's why it's often good, instead of thinking about roots and double roots and so on, just to think about how it factors. Because you think of a polynomial as having the roots r1 through rn if it factors like this. And some of the factors might be the same, but it'll factor like that. More questions? And I know some of these things sort of sound simple, and they're actually not. They're really not. That's why I'm sort of making heavy weather out of it. Now here's something cool. How do the coefficients of a polynomial depend upon the roots? Suppose you have a polynomial like this with coefficients, and you can factor it into this product of roots. What can we say about the different coefficients? What is a0, for example? What is a0? In terms of these things, if you multiply this out, what are you going to get for a0? It's not quite the product of all the roots, but it's very close. It's not quite a times the product of all the roots either. What we have is the first term is going to be an, because an times all of these x's. The next term, I'll let you sort of think about this, but if you multiply all this out, what you're going to get is negative an times the sum of all of these r's. Because there's, if you consider all of these, when are you going to get x to the n minus 1? Well, when you've taken n minus 1 x's and you've taken one of these r's, one of these negative r's. And one of these negative r's, and all of these together give you this sum. Likewise, for the next degree term, you're going to get r1 times r2, r1 times r3, and all the possible pairs of roots summed together. And then all the way out here, the final term is going to be all of these roots multiplied together, but they're negatives too. So it's negative 1 to the n. The sign keeps flipping. It's negative, positive, negative, positive. So negative 1 to the n times the product of all the roots times this leading coefficient down in front. That means that we can actually write each of these coefficients once we've normalized by an. Often an will be 1, but I just wanted to write this down here. So often the leading term will have coefficient 1. So this would just be a sub n minus 1. The first one is going to be negative the sum of the roots. The next one is going to be positive the sum of all the products of 2 of the roots. The next one is going to be negative the sum of the triples of the roots, and all the way down to the last one, the constant term, which is going to be plus or minus, depending upon the number, depending on whether n is even or odd, the product of all the roots. These are called Vieta's formulas, and they're super useful sometimes. Let's see a way in which they're useful. Suppose the roots of a polynomial, this polynomial x cubed minus 2x squared plus 1, are given as r1, r2, and r3. What is the sum of them? And what is the sum of the reciprocals of them? First, what's the sum? Yes, so the sum is 2. And that's because with the formulas on the previous slide, we had this coefficient over this coefficient is negative the sum of the roots. So since the first coefficient is 1, we know that r1 plus r2 plus r3 is the negative of the coefficient on x squared, which is the negative of negative 2. So r1 plus r2 plus r3 equals 2. Cool. Now, the next one is tricky. How do we do it? Yeah, so there are a couple of ways to do it. One way is to substitute in y equals 1 over x, which is clever. Another clever way to do it is to get the same common denominator. So the sum of the reciprocals is equal to this over r1, r2, r3, which looks a bit messy until we remember that we actually saw that already. We know that the sum of the pairs of the products of pairs is actually going to be something that we know from Vieta's formulas. And this is something we also know. So the r1, r2, r3 is going to be the constant coefficient, so this 1, times negative 1 to the 3. So that's going to be negative 1. And this is going to be the coefficient on x. Remember on the previous couple of slides before, we had this. So this sum of the products of pairs is just going to be this coefficient here, which is the coefficient on x. And so we have 0 here over -1. So we end up with the sum of the reciprocals actually being 0. And if you're curious what these roots are, they actually are real roots in this case. There's 1, and there's the golden ratio, and there's the conjugate of the golden ratio, which we saw before. So you could actually have calculated what the roots are, but for a larger polynomial, you definitely wouldn't want to do that. So here are some useful factorizations. And these are things like, I don't often say memorize something, but I think that these are good to memorize. They're just useful in a lot of situations. They're super easy to memorize. You should never really you shouldn't try to memorize math in general, but these are things that you could derive. Like you can easily prove these things just by multiplying them out, but they're not, they will turn up. So it's useful to sort of have them handy. First one, x squared minus y squared equals x minus y times x plus y. This is so useful. If you have a difference of squares, you can write it as the product of x minus y and x plus y. Next one, x to the n minus 1 is equal to x minus 1 times the sum of all of these things. And so this is like telescoping sums. When we saw that in the induction lecture, when we saw different things that canceled, if you try to multiply this out, you'll see that this is telescoping sums. Like x minus 1 times this is x to the n minus x to the n minus 1. And the next one is x to the n minus 1 minus x to the n minus 2. And they all cancel, and you only get the first one and the last one. It's really cute. The last one is x cubed plus y cubed. This is not as useful as the other two, but x cubed plus y cubed can be written like this. Given that, what could you do with x to the 6 minus 1? So we could factor it using the second equation. We can actually also factor it using the first equation. Because we can factor it as x cubed squared minus 1 squared. So we can do this. But then, what do we do now? Well, we know this first thing can be written using the second nice factorization, and the third thing can be written using the last one. Third thing can be written using the last one if you take y equals to 1. So these two come from decomposing this using the second equation, and these last two come from decomposing x cubed plus 1 using the third equation. It's just an example of something that you might do with these factorizations. And now, and yes, you could just use the third equation. You could absolutely do that. You could even factor some more. You could factor down a linear factors, but there's this is just, you should see some of these factorizations when you see some of these polynomials. It should just help you to sort of work with polynomials. Now here is a deep question. What are the n complex roots of x to the n minus 1? These are also called roots of unity. Now, to do this, let's look at the trigonometric form. We're going to find an x equals some r and some theta. And what we'd like is for, this should be x to the n minus 1 equals 0. So we would like 1 to be equal to x to the n. That's what it means to be a root of this polynomial. So we would like 1 to equal this. Remember, again, in the trigonometric form, radii multiply and angles add. So we have r to the n and cosine of n times theta if we're multiplying this x by itself n times. So what can we do with that? Well, that's going to mean that r is going to equal 1 because we would like these to be equal to 1, and we would like we'd like n theta to be some multiple of 360 degrees. Because we'd like all of this to just be equal to 1. 1 to the n times 1. Now, how can n theta be equal to 360 degrees? Well, there are if there are going to be n different numbers between 0 and 360 degrees, where n theta is a multiple of 360. In the case of n equals 1, there's just this one, 0. 0 times n equals 1 is a multiple of 360, it's 0. In n equals 2, we have 2, 0 and 180 degrees. 2 times 180 degrees is also a multiple of 360. In the case of n equals 3, we have 3 of them. This, angle 0, angle 360 over 3, and angle 2 times 360 over 3. So 120 and 240. All of these multiplied by 3 will give you a multiple of 360 degrees. And likewise, and you can see that these form regular polygons. And they're all on the unit circle because radius is 1. So these are the complex roots of unity for different numbers n. Let's look at a couple examples. If n equals 2, then we know that theta is equal to 0 or 180 degrees. And so that means that x is equal to plus or minus 1, because it's either angle 0, so on the positive side of the x-axis, or angle 1 on the negative side of the x-axis. In the case of n equals 4, then we have these roots of unity: angle 0, 90, 180, or 270. And so x is going to be the corresponding complex numbers: 1, a positive x-axis, I, positive y-axis, -1, negative x-axis, and negative I, negative y-axis. And this lines up with what we saw earlier, which is that I to the fourth is going to be equal to 1. That's because I is one of the fourth roots of unity of 1. Let's end on a problem. I'll leave inequalities until next time. What are the roots of this polynomial? What are some ways we can go about this? Yeah, so we can use that factorization from earlier. We know that x to the fifth minus 1 is x minus 1 times this. So how can we use that? We want to find the roots of this. Do we know anything about the roots of anything else here? Yeah, so we know that 1 is a root. There isn't going to be a square root of 5 involved, or at least not like that. Yeah, so some people are suggesting we know the roots of these are the roots of unity. And there is this nice geometric picture of that. When is this equal to 0? Well, it's equal to 0 when either this term is equal to 0 or this term is equal to 0. So that's going to mean that the roots of this are when this is equal to 0, that's when x equals 1, that's the only root, or when this equals to 0. So the roots of this polynomial that we care about must be the same as the roots of x to the fifth minus 1, with the exception of x equals 1. Now we know that the fifth roots of unity are given by cosine of theta plus I sine theta for theta equals these various angles. And why do I get these angles? Well, these are just the angles from that pentagon from earlier here. This is the n equals 5 case. These are equally spaced out. 5 times any of these angles will give us a multiple of 360 degrees. So 72 is just 360 degrees over 5. And so the answer is just going to be cosine of theta plus I sine theta for theta equals any of these, but we leave out one of them. Which one do we leave out? We leave out the one that corresponds to x equals 1. X equals 1 is when theta equals 0 degrees. So the answer is just all of these others. And how many do we have? We have 4 of them, which is exactly what we want. We have a degree 4 polynomial, so we expect it to have 4 roots. These are the 4 roots. Now you actually can solve for these in like, there's a nice form for this, what cosine and sine of 72 degrees are. I'm not going to go into that. This is totally sufficient for us. We know basically what they are in trigonometric form. Okay. I will leave anything else until another class, and we will work on number theory next class. I'll stick around for a few minutes if people have any questions.